What existed before time itself? It's a question that pushes the boundaries of human understanding, forcing us to confront the very edges of reality. Think of the universe as a blank canvas, utterly empty, silent, and waiting for that first brushstroke of creation. But what sparked that stroke? Was there a moment when nothing became everything? Or has the universe always been, stretching infinitely into the past and future? These are the mysteries we're diving into today. Unraveling the origins of the cosmos isn't just about science, it's about challenging the way we see existence itself. From the Big Bang to theories of multiverses and quantum fluctuations, we'll explore the most groundbreaking ideas that attempt to explain where it all began. And along the way, we'll uncover questions that might reshape how you think about time, space, and your place in the universe. So, if you're ready to step into the unknown and explore the cosmic origins of everything, let's begin this journey together. Imagine a moment so profound, so unimaginably vast, that it set the stage for everything we know and everything we don't. This is the story of the Big Bang, the most widely accepted explanation for how our universe came to be. Picture a single point smaller than the tip of a pin, yet containing all the energy, matter, and potential of the cosmos. This is what scientists call a singularity, a state of infinite density and temperature where the laws of physics as we know them break down. From this singularity, the universe burst into existence in an unfathomable explosion, not into space but of space. Time itself began ticking. Matter and energy erupted, expanding faster than the speed of light, laying the foundation for stars, galaxies, and eventually us. As Stephen Hawking once put it, the Big Bang wasn't an explosion in space, it was the expansion of space itself. It's a concept that challenges our intuition, yet it's the cornerstone of modern cosmology. But here's the twist: while the Big Bang theory gives us a starting point, it doesn't tell us everything. What caused the singularity? What existed before the Big Bang? These questions linger unresolved, like puzzle pieces that don't quite fit. The Big Bang is a powerful framework, but it's also a doorway to deeper mysteries, inviting us to explore what lies beyond the edges of our understanding. But what if the Big Bang wasn't the true beginning? What if it was just one moment in an endless cosmic cycle, or perhaps a single event in a much larger, more mysterious multiverse? This is where the question of what existed before the Big Bang becomes one of the most tantalizing puzzles in all of science. While the Big Bang marks the birth of our observable universe, it doesn't necessarily explain what, if anything, came before. Some theories suggest that the universe could have emerged from quantum fluctuations, tiny ripples in the fabric of reality, that somehow sparked the expansion we now call the Big Bang. Imagine a calm ocean suddenly disturbed by a single ripple growing into a wave. Could the universe have started as a similar kind of cosmic ripple? Others propose the idea of a multiverse, where our universe is just one bubble in a vast cosmic foam. Picture a pot of boiling water with bubbles constantly forming, growing, and popping. In this analogy, our universe is one of those bubbles, and the Big Bang was the moment our bubble began to expand. But what about the other bubbles? Could there be countless other universes, each with its own unique laws of physics? Then there's the cyclic model, championed by physicists like Roger Penrose. This idea suggests that the universe goes through endless cycles of expansion and contraction, with each Big Bang followed by a big crunch, only to start all over again. It's like a cosmic heartbeat pulsing through eternity. Penrose's work even hints at the possibility of detecting evidence from a previous universe in the faint echoes of the cosmic microwave background radiation, the afterglow of the Big Bang. So, what does all this mean for the idea of a pre-Big Bang universe? If these theories hold true, then the Big Bang might not be the ultimate beginning but rather a gateway, a transition point between one cosmic era and the next. And if that's the case, then the mysteries of the early universe might just be the tip of the iceberg. What lies beyond the Big Bang could rewrite everything we thought we knew about time, space, and the very nature of existence itself. Picture a universe so small, so dense, and so hot that it exists on a scale almost impossible to comprehend. This is the Planck Epoch, the first sliver of time after the Big Bang, lasting just 10 to the power of -43 seconds. At this moment, the universe was a seething cauldron of energy where the rules of gravity and quantum mechanics collided in ways we still struggle to understand. Quantum gravity, the elusive theory that seeks to unite Einstein's general relativity with quantum physics, reigned supreme here. But here's the catch: we don't yet have a complete framework to describe it. Our current understanding of physics breaks down in this extreme environment, leaving scientists with more questions than answers. Imagine trying to study a storm by only looking at the ripples it leaves behind. That's the challenge we face with the Planck Epoch. The extreme conditions of this era, temperatures reaching 10 to the power of 32 degrees Celsius, densities beyond imagination, make it impossible to recreate or observe directly. It's like trying to solve a puzzle with half the pieces missing. Without a unified theory of quantum gravity, we're left peering into the fog of the early universe, piecing together clues from later cosmic events. To make sense of this chaos, think of the universe during the Planck Epoch as a quantum soup, a bubbling, churning mixture where particles and forces were indistinguishable from one another. Gravity, the force that shapes galaxies and bends light, was just one ingredient in this primordial stew, entangled with the other fundamental forces in ways we can only theorize. It's a realm where space and time themselves lose their familiar meaning, becoming warped and fluctuating on the tiniest scales. But as wild as the Planck Epoch was, it didn't last forever. Out of this quantum chaos emerged the seeds of order, setting the stage for the next dramatic chapter in cosmic history, cosmic inflation. This explosive expansion, which began just after the Planck Epoch, stretched the universe exponentially, smoothing out irregularities and laying the groundwork for the structures we see today. It's as if the universe took a deep breath and then exhaled, transforming from a chaotic quantum soup into something far more recognizable. And it's here that our story of cosmic origins truly begins to take shape. Picture this: a universe so small it could fit in the palm of your hand, suddenly exploding outward faster than the speed of light. This isn't science fiction, it's cosmic inflation, the theory that describes how the universe underwent an unimaginably rapid expansion just fractions of a second after the Big Bang. In that fleeting moment, the fabric of space itself stretched exponentially, smoothing out irregularities and setting the stage for everything we see today. But why does this idea matter, and how does it solve some of the biggest puzzles in cosmology? One of the key problems inflation addresses is the horizon problem. Imagine looking out into the night sky in opposite directions. The light from those distant regions has traveled billions of years to reach us, yet they appear remarkably similar in temperature and structure. Without inflation, there wouldn't have been enough time for these regions to interact and reach equilibrium. But during inflation, the universe expanded so quickly that these distant areas were once much closer together, allowing them to share a common temperature before being stretched apart. It's like blowing up a balloon. No matter how far apart 2 points are now, they were once right next to each other. Another puzzle inflation solves is the flatness problem. The universe appears to be incredibly flat on large scales, meaning its geometry follows the rules of Euclidean space. Without inflation, this level of flatness would require an impossibly fine-tuned starting condition. But inflation acts like a cosmic iron, smoothing out any curvature and stretching the universe into the flat shape we observe today. It's as if you crumpled a piece of paper and then stretched it so large that the wrinkles became imperceptible. This groundbreaking idea was first proposed by physicist Alan Guth in the late 1970s. Guth's work showed that a brief period of rapid expansion could explain not only these cosmological puzzles, but also the distribution of galaxies and the seeds of cosmic structure we see today. His theory fundamentally changed the way we think about the early universe. But here's the intriguing question: what could have triggered such an extraordinary event? What force or mechanism caused the universe to expand so dramatically in such a short time? And perhaps even more mysterious, what existed before inflation? These questions take us to the very edge of our understanding, where the known laws of physics begin to blur into the unknown. What if our universe isn't the only one out there? What if, beyond the edges of what we can see, there are countless other universes, each with its own unique set of rules and realities? This is the essence of the multiverse hypothesis, a bold idea that suggests our universe is just one small piece of a much larger cosmic tapestry. Picture this: instead of a single universe, there could be an infinite number of them, each existing like a bubble in a vast cosmic foam. These bubble universes might have formed during the rapid expansion of space known as inflation, with each bubble containing its own distinct physics, chemistry, and even life. Some could be eerily similar to ours, while others might be so alien that they defy comprehension. And then there's the idea of parallel dimensions, universes that exist alongside ours, separated by dimensions we can't perceive. It's like walking through a hall of mirrors where every reflection is a slightly different version of reality. To get a sense of how this might work, let's try a thought experiment. Imagine a library with an infinite number of books. Each book represents a universe, and every page within it describes a different set of physical laws. Some books might have pages where gravity is stronger or where time flows backward. Others could contain universes where life evolves in ways we can't even imagine. The multiverse hypothesis suggests that all these possibilities exist somewhere in some form. Physicists like Max Tegmark have taken this idea even further, proposing different levels of multiverses. Tegmark's framework includes everything from universes beyond our cosmic horizon to those governed by entirely different mathematical structures. It's a mind-bending concept, but one that challenges us to rethink our place in the cosmos. And here's where things get even more fascinating. If the multiverse is real, what does that mean for us? Are we just one of countless versions of ourselves, living out different lives in different realities? Or is our universe special, somehow fine-tuned for life in a way that others aren't? These questions aren't just scientific, they're deeply philosophical, forcing us to confront what it means to exist in a cosmos that might be far stranger and more expansive than we ever imagined. As we explore these ideas, we're not just pushing the boundaries of science, we're also grappling with the very nature of reality itself. And that's what makes the multiverse hypothesis so compelling. It's not just a theory about the cosmos, but a window into the infinite possibilities of existence. What if the universe isn't just the three dimensions we see and the one we experience as time? What if there are hidden layers, dimensions beyond our perception, that hold the key to understanding everything? This is where string theory steps in, a bold and mind-bending framework that reimagines the very fabric of reality. At its core, string theory suggests that the fundamental building blocks of the universe aren't tiny particles, but incredibly small, vibrating strings. Think of these strings like the notes on a cosmic guitar, each vibration producing a different particle or force. It's a symphony of existence where every string plays a unique role in shaping the universe. But here's where it gets even more fascinating. String theory doesn't stop at the familiar dimensions we know. It proposes that there are at least 10 dimensions, maybe even 11. These extra dimensions are curled up so tightly, so infinitesimally small, that we can't perceive them in our everyday lives. Imagine a garden hose lying on the ground. From a distance, it looks like a one-dimensional line, but up close, you see it's actually a three-dimensional cylinder. In the same way, these higher dimensions could be all around us, just too tiny for us to notice. Now, string theory isn't without its challenges. One of the biggest hurdles is that it's incredibly difficult to test experimentally. The scales involved are so small, and the energies required to probe them so high that our current technology falls far short. It's like trying to hear a whisper in the middle of a thunderstorm. But despite these obstacles, string theory remains one of the most promising candidates for a theory of everything, a framework that could unify all the forces of nature, from gravity to electromagnetism. And here's the kicker: string theory might even hold clues about what happened before the Big Bang. If the universe began as a singularity, a point of infinite density and temperature, string theory suggests that such a singularity could have been the result of higher dimensional interactions. Perhaps our universe is just one note in a much larger cosmic orchestra, with strings vibrating in dimensions we've yet to fully comprehend. But what if the fabric of space-time isn't smooth and continuous like we've always imagined? Enter loop quantum gravity, a bold alternative to string theory that rewrites the rules of how we understand the universe's most fundamental layers. Instead of viewing space-time as an endless, unbroken expanse, loop quantum gravity proposes something far more intriguing. A universe built from tiny, indivisible loops, like threads woven into a cosmic tapestry. These loops are the building blocks of space-time itself, giving it a discrete, pixelated structure at the tiniest scales imaginable. Picture this: if you could zoom in on space-time with a microscope powerful enough, you wouldn't see a smooth surface. Instead, you'd find a network of interconnected loops, each one representing the smallest possible unit of space and time. It's like imagining the universe as a digital image, where every pixel is a loop, and together they create the picture we see. This radical idea challenges our traditional notions of continuity and opens up a whole new way of thinking about the cosmos. One of the most fascinating implications of loop quantum gravity lies in its take on the Big Bang. Instead of a singularity, a point of infinite density where the laws of physics break down, this theory suggests something entirely different: a cosmic bounce. Imagine the universe not as a single explosive beginning, but as a cycle. Before our universe expanded, it could have been contracting, reaching a point of maximum density before springing back outward. This bounce offers a way to avoid the perplexing singularity, suggesting that the Big Bang might not have been the absolute start, but rather a transformative moment in an ongoing cosmic rhythm. So, if the Big Bang wasn't the beginning, what came before the bounce? What lies beyond that moment of transformation? These questions push us to the edge of our understanding, inviting us to explore the mysteries that loop quantum gravity brings to light. As we delve deeper into this theory, we're not just rewriting the rules of space-time, we're reimagining the very origins of existence itself. What if our universe, with all its vastness and complexity, is just a projection, a cosmic hologram where everything we see and experience is merely a shadow of a deeper reality encoded on a distant boundary? This is the essence of the holographic principle, a groundbreaking idea that redefines how we think about space, time, and even the origins of existence itself. Imagine a hologram, a two-dimensional surface that, when illuminated, creates the illusion of a three-dimensional object. Now, picture the entire universe working in a similar way. According to this principle, all the information needed to describe our three-dimensional reality could be stored on a two-dimensional boundary, like a cosmic film strip. It's as if the universe itself is a grand illusion, a projection of data from the edges of reality. This idea didn't come out of nowhere. It emerged from the work of physicists like Leonard Susskind, who explored the strange connections between black holes and quantum mechanics. Black holes, those mysterious regions where gravity is so intense that not even light can escape, seem to hold a clue. Susskind and others discovered that the information swallowed by a black hole isn't lost forever. It's somehow encoded on the black hole's surface, its event horizon. This revelation sparked a radical idea. What if the entire universe operates on a similar principle? What if the fabric of space and time isn't the fundamental layer of reality, but just a projection of information stored on some distant two-dimensional boundary? The implications are staggering. If the holographic principle is true, it challenges everything we thought we knew about space and time. Space isn't just an empty stage where events unfold. It's a dynamic, emergent property of the universe's underlying information. Time, too, might not flow in the linear way we experience it. Instead, it could be an illusion, a byproduct of how information is processed and projected. This shifts our understanding of the cosmos from a physical, tangible framework to something far more abstract and interconnected. But what does this mean for the origins of the universe? Could the holographic principle hold the key to understanding what happened before the Big Bang? Some physicists speculate that if the universe is holographic, then the Big Bang itself might not have been the beginning of everything, but rather a transformation, a moment when the universe's underlying information was reorganized and projected into the reality we know today. In this view, the pre-Big Bang universe could have been a different kind of holographic projection, a state of existence we're only beginning to imagine. The holographic principle doesn't just challenge our understanding of the universe, it invites us to rethink the very nature of reality itself. Picture this, the universe as a vast, intricate tapestry. But here's the twist: what we see, the stars, planets, and galaxies, makes up only about 5% of everything that exists. The rest, it's hidden in the shadows, composed of two mysterious forces, dark matter and dark energy. Together, they dominate the cosmos, yet they remain invisible, undetectable by traditional means. So what exactly are they, and why do we believe they're out there? Let's start with dark matter. Think of it as the universe's unseen scaffolding. We can't see it, but we know it's there because of its gravitational pull. Take galaxies, for instance. They spin so fast that, according to the laws of physics, they should fly apart, but they don't. Something invisible, dark matter, holds them together, acting like cosmic glue. Without it, galaxies as we know them wouldn't exist. Yet, despite its crucial role, dark matter remains one of the greatest puzzles in science. What is it made of? We don't know. Could it be particles we've yet to discover? Possibly. Experiments deep underground and in space are hunting for clues, but so far, dark matter has eluded us. Then there's dark energy, an even more perplexing force. While dark matter pulls things together, dark energy does the opposite. It pushes the universe apart. In the late 1990s, astronomers made a shocking discovery. The universe isn't just expanding, it's accelerating. Something is driving this cosmic speed up, and we call it dark energy. It's thought to make up about 68% of the universe, dwarfing even dark matter. But what is it? Is it a property of space itself, or does it emerge from some unknown field? The truth is, we're still grasping at answers. Together, dark matter and dark energy shape the fate of the cosmos. They dictate how galaxies form, how the universe expands, and even how it might end. Yet, for all their influence, they remain shrouded in mystery. scientists are working tirelessly to uncover their secrets. From underground detectors searching for dark matter particles to telescopes mapping the universe's expansion, the quest continues. But here's the big question. Could these invisible forces hold the key to understanding the very origins of the universe? Could they be remnants of the cosmic dawn, clues to what happened before the Big Bang? The answers might lie just beyond our reach, waiting to reshape everything we think we know. Imagine looking at a photograph of the universe when it was just a newborn, only 380,000 years old. That's essentially what the cosmic microwave background, or CMB, allows us to do. Often described as the afterglow of the Big Bang, the CMB is the oldest light in the cosmos, a faint whisper of energy that has been traveling through space for over 13.8 billion years. It's like finding a cosmic time capsule, offering us a direct glimpse into the universe's earliest moments. When we map the CMB, what we see is a stunningly detailed snapshot of the universe in its infancy. Tiny fluctuations in temperature, barely a fraction of a degree, reveal the seeds of everything we see today: galaxies, stars, and even the vast cosmic web that connects them. These subtle variations, often visualized as a colorful, speckled map, are the fingerprints of density differences in the early universe. They show us where matter began to clump together, setting the stage for the structures we observe now. But the CMB isn't just a pretty picture, it's a cornerstone of modern cosmology. Its existence and precise properties provide some of the strongest evidence for the Big Bang theory. The fact that this radiation is nearly uniform in all directions, with those tiny fluctuations, aligns perfectly with the idea that the universe began as an incredibly hot, dense point and has been expanding ever since. What's more, the CMB also supports the concept of cosmic inflation, a rapid expansion of the universe in the tiniest fraction of a second after the Big Bang. Inflation explains why the universe looks so smooth on large scales, while still having those small irregularities that eventually grew into galaxies. And here's where it gets even more fascinating. The CMB doesn't just confirm what we already know, it also challenges us to dig deeper. By studying its patterns, scientists have been able to uncover clues about the universe's composition, including the mysterious dark matter and dark energy that make up most of its content. It's like decoding a cosmic message, one that tells us not only about where we came from, but also where we might be headed. So, what does this ancient light reveal about the universe's infancy? It shows us a time when the cosmos was a hot, dense soup of particles before stars or galaxies even existed. It's a reminder that everything we see today, every planet, every star, every galaxy, started from those tiny ripples in the fabric of space and time. And while the CMB may seem like a relic of the past, it's also a living testament to the universe's ongoing story, one that we're only just beginning to understand. What if the universe's first structures weren't stars or galaxies, but something far more mysterious? Enter primordial black holes, cosmic seeds that may have formed in the chaotic moments after the Big Bang. Unlike the black holes we know today, born from collapsing stars, these primordial ones could have emerged from tiny, dense fluctuations in the early universe. Think of them as the universe's first architects, silently shaping everything that came after. These ancient black holes might have played a critical role in how galaxies formed. Picture a cosmic web with galaxies strung like beads on invisible threads. Primordial black holes could have acted as anchors, drawing matter together and creating the gravitational scaffolding for galaxies to take shape. Some scientists even suggest they could explain the elusive nature of dark matter. If these black holes are scattered throughout the cosmos, they might account for the invisible mass that holds galaxies together without emitting any light. The search for these primordial relics is ongoing and thrilling. astronomers are scanning the skies for traces of their existence, from subtle gravitational effects to bursts of radiation. It's like hunting for cosmic fossils, ancient remnants that could rewrite our understanding of the universe's origins. But here's the real question. If primordial black holes are out there, what do they tell us about the universe's earliest moments? Were they the spark that set the cosmos in motion, or just one piece of a much larger puzzle? As we dig deeper into their mysteries, we're not just uncovering the past, we're peering into the very foundation of reality itself. Symmetry is one of the most profound ideas in physics, and it played a crucial role in shaping the early universe. At its core, symmetry is about balance and harmony, the idea that certain properties remain unchanged even as the universe evolves. In the moments just after the Big Bang, the universe was incredibly hot and dense, and it was governed by a kind of perfect symmetry. All the fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single, all-encompassing force. Particles and energy were indistinguishable, existing in a state of perfect equilibrium. But as the universe expanded and cooled, that symmetry began to break. Think of it like water freezing into ice. When water is liquid, it looks the same in every direction, it's symmetrical. But when it freezes, the molecules align in specific patterns, breaking that symmetry. Similarly, as the universe cooled, the unified force split into the distinct forces we observe today. This process, known as symmetry breaking, is what allowed matter and energy to take on the forms we recognize. One of the most famous examples of symmetry breaking comes from the Higgs field, a concept proposed by physicist Peter Higgs and his colleagues in the 1960s. The Higgs field permeates the entire universe, and when particles interact with it, they gain mass. Without this field, particles would zip around at the speed of light and atoms, and life as we know it couldn't exist. The discovery of the Higgs boson in 2012 confirmed this theory, earning Higgs and his team the Nobel Prize. But what about the universe before the Big Bang? Could symmetry have played a role even then? Some theories suggest that the pre-Big Bang universe might have been in a state of maximum symmetry, a kind of cosmic blank slate. As this primordial symmetry began to unravel, it could have set the stage for the explosive birth of our universe. This idea opens up fascinating questions about how symmetry might have shaped not just the universe we see, but the very fabric of existence itself. Symmetry, in a way, is the hidden architect of reality. It shapes the forces that govern the cosmos, the particles that make up matter, and even the structure of space and time. And as we explore the mysteries of the early universe, it's clear that understanding symmetry is key to unraveling the story of how everything began. Time is one of the most familiar yet mysterious forces in the universe. It flows in one direction, carrying us from the past into the future, and we've come to call this the arrow of time. But what exactly gives time its direction? The answer lies in a concept called entropy, which is essentially a measure of disorder in the universe. Picture a freshly brewed cup of coffee, steam rising, the aroma filling the room. Over time, the heat dissipates, the coffee cools, and the molecules spread out into the air. That's entropy at work, and it's a one-way street. The universe, it seems, has a preference for moving from order to disorder, and this is what drives the arrow of time. Now imagine if time could run backward. What would that look like? A shattered cup of coffee reassembling itself, steam condensing back into liquid, and the aroma retreating into the cup. It sounds bizarre, doesn't it? Yet, the laws of physics don't explicitly forbid such a scenario. The difference between past and future, then, isn't about the laws themselves, but about the flow of entropy. This strange asymmetry is baked into the fabric of our universe, and it's deeply connected to the Big Bang. The Big Bang wasn't just the beginning of space and matter, it was also the beginning of time as we know it. At that moment, the universe was in an incredibly ordered state, with all its energy tightly packed together. As it expanded, entropy began to increase and the arrow of time started pointing forward. But here's where things get even more intriguing. If the Big Bang marked the start of time, what came before it? Did time exist at all, or is it something that emerged alongside the universe? These questions push us to the very edge of what we can comprehend, challenging our understanding of reality itself. Now, picture the early universe as a vast, empty canvas, but not entirely smooth. Instead, it's teeming with tiny, unpredictable ripples, quantum fluctuations. These fluctuations, though incredibly small, were the seeds of everything we see today. Think of them like ripples on a calm pond. When you toss a stone into the water, the ripples spread out, creating patterns. In the same way, these quantum ripples in the early universe set the stage for the formation of galaxies, clusters, and the cosmic web we observe now. But how did something so small lead to something so enormous? Here's where things get fascinating. During the rapid expansion of the universe, known as inflation, these tiny quantum ripples were stretched across vast distances. What started as microscopic variations in density grew into the large-scale structures we see today. It's like blowing up a tiny speck on a balloon. As the balloon expands, the speck becomes a noticeable mark. These fluctuations didn't just disappear after inflation. They left their fingerprints everywhere, especially in the cosmic microwave background, or CMB. This faint glow, often called the universe's first light, carries the imprint of those early quantum ripples. Scientists study the CMB like a cosmic treasure map, decoding the patterns to understand how the universe went from a smooth, hot soup of particles to the intricate, structured cosmos we inhabit. What's truly remarkable is that these quantum fluctuations connect us directly to the universe's origins. They're not just random noise, they're the echoes of the very first moments of existence, the whispers of a time before stars, galaxies, or even atoms. By studying them, we're peering back into the dawn of time itself, unraveling the story of how everything began. And as we continue to explore, we're reminded that even the tiniest fluctuations can lead to the grandest of cosmic designs. Imagine the universe as a vast, empty canvas waiting for its first brushstrokes. But instead of a painter, the artist here is something far more subtle: quantum fluctuations. These tiny, random ripples in the fabric of space-time might sound insignificant, but they hold the key to understanding how our universe grew into the intricate web of galaxies and cosmic structures we see today. And the process that made this possible: cosmic inflation. Inflation is like a cosmic magnifying glass, stretching those tiny quantum ripples across unimaginable distances. Picture this: during the universe's earliest moments, space itself expanded faster than the speed of light. This rapid expansion didn't just make the universe bigger, it amplified those minuscule quantum fluctuations, turning them into the seeds of galaxies, galaxy clusters, and even the vast cosmic voids we observe. Without inflation, those fluctuations would have remained too small to matter, lost in the vastness of the cosmos. But here's where it gets fascinating. The patterns we see in the universe today, the way galaxies group together in filaments and clusters, separated by enormous empty spaces, are echoes of those early quantum ripples. It's as if the universe took a snapshot of those tiny imperfections and stretched them into the blueprint for its entire structure. And this process wasn't random. It followed precise laws of physics, leaving behind a cosmic fingerprint that scientists can still detect in the faint glow of the cosmic microwave background. What does this mean for the universe's earliest moments? It tells us that even in the tiniest fractions of a second after the Big Bang, the universe was already setting the stage for everything that would come later. Inflation didn't just shape the universe, it sculpted its destiny, creating the conditions for stars, planets, and ultimately, life itself. So the next time you look up at the night sky, remember, the galaxies above owe their existence to those quantum ripples, magnified by the power of inflation billions of years ago. Picture this: the universe, once expanding faster than the speed of light, suddenly slows down. It's like a balloon that's been inflating at an incredible rate, only to stop mid-burst. This moment, known as the end of cosmic inflation, was a turning point in the story of our universe. It marked the shift from an era of rapid, exponential growth to the hot, dense state that would eventually give rise to everything we see today: the stars, galaxies, and even the atoms that make up you and me. But what caused this dramatic slowdown? What made the universe switch gears from inflation to the hot Big Bang phase? The answer lies in the energy field that drove inflation in the first place. As this field began to decay, it released its stored energy, heating up the cosmos and filling it with particles. Think of it like a pot of water coming to a boil. The energy that once fueled inflation was now transforming into the building blocks of matter and radiation, setting the stage for the universe as we know it. This transition wasn't instantaneous. It happened over a fraction of a second, but in that brief window, the universe underwent a profound transformation. The once smooth, uniform fabric of space-time began to ripple with tiny fluctuation seeds that would grow into the vast cosmic structures we observe today. These fluctuations, born from the quantum jitters of the inflationary field, became the blueprint for everything from the smallest galaxies to the largest superclusters. So what triggered the end of inflation? It's a question that still puzzles scientists. Some theories suggest it was a natural decay of the inflationary field, while others propose more exotic mechanisms. Whatever the cause, this pivotal moment set the universe on a new path, one that would lead to the formation of stars, planets, and eventually life itself. It's a reminder that even the most chaotic beginnings can give rise to something extraordinary. But before the first stars ignited and galaxies began to form, the universe was a swirling, chaotic sea of energy and particles. This primordial state, known as quark-gluon plasma, existed in the earliest moments after the Big Bang. Picture it as a cosmic soup, hotter and denser than anything we can imagine, where quarks and gluons, the building blocks of protons and neutrons, roamed freely, unbound by the forces that hold matter together today. At temperatures reaching trillions of degrees, this plasma was the universe's first form of matter. It was a time when the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were still merging into a single, unified force. To recreate this extreme environment, scientists use powerful particle colliders like the Large Hadron Collider. By smashing heavy ions together at nearly the speed of light, they've been able to produce tiny droplets of quark-gluon plasma, giving us a glimpse into the universe's fiery infancy. These experiments reveal a fascinating truth. As the universe expanded and cooled, the quark-gluon plasma began to transform. Quarks and gluons gradually combined, forming protons and neutrons, the seeds of all matter we see around us. This transition marked the first step in the universe's journey from a seething, chaotic state to the structured cosmos we know today. But how exactly did this happen? And what forces governed the delicate balance that allowed matter to emerge? The answers lie in the intricate dance of physics that unfolded in those first fleeting moments. As the universe continued to cool and expand, a pivotal moment arrived, one that would set the stage for everything we know today. This was the era when quarks, those tiny, fundamental particles, began to combine in a process that would ultimately give rise to protons and neutrons. Picture this: quarks are like the individual Lego pieces of the cosmos, each one brimming with potential. But it's only when they snap together that they form something far more significant. That's exactly what happened in the early universe, thanks to an extraordinary force, the strong nuclear force. This force, which is one of the four fundamental forces in nature, acts like a cosmic glue. It's incredibly powerful, binding quarks together so tightly that they can't escape each other's pull. Think of it as the ultimate teamwork, quarks joining forces, three at a time, to create protons and neutrons. Without this force, the building blocks of matter as we know it simply wouldn't exist. It's like trying to build a house without nails or mortar. The structure just wouldn't hold. But why is this so important? These newly formed protons and neutrons weren't just random particles floating around. They were the first stable pieces of matter in the universe, the seeds from which everything else would grow. As the universe continued to cool, these particles began to cluster together, setting the foundation for the first atomic nuclei. It's a bit like how a single snowflake might seem insignificant, but when millions come together, they form a snowstorm, a force to be reckoned with. So what does this mean for the early universe? How did these protons and neutrons shape its future? Well, their formation marked the beginning of a delicate dance, one that would eventually lead to the creation of atoms, stars, and galaxies. But that's a story for another moment. For now, let's just marvel at how these tiny particles, forged in the heat of the early cosmos, became the cornerstone of everything we see around us, and even the stuff we can't see. Imagine the universe just moments after the Big Bang, a seething, unimaginably hot soup of energy and particles. In this chaotic, dense environment, the first seeds of matter began to take shape. This is the story of Big Bang Nucleosynthesis, the cosmic process that gave birth to the simplest elements in existence. But how did it happen? The key lies in the extreme conditions of the early universe. Temperatures were so high, billions of degrees, that particles like protons and neutrons couldn't even bind together. But as the universe expanded and cooled, something remarkable occurred. Within the first few minutes, the temperature dropped just enough for protons and neutrons to combine, forming the nuclei of the lightest elements. Hydrogen, the simplest and most abundant element, emerged first. Its nucleus is just a single proton. Then came helium with 2 protons and 2 neutrons. These 2 elements became the building blocks of everything we see today. But here's the catch: the entire process lasted only about 20 minutes. After that, the universe cooled too much for further reactions to occur. That brief window was all it took to create the raw materials for stars, galaxies, and eventually us. Think of it like a cosmic forge. In those early moments, the universe acted as an immense furnace, fusing particles into the first elements. But this forge didn't produce everything. Elements heavier than helium like carbon, oxygen, and iron wouldn't form until much later inside the hearts of stars. For now, the universe was left with a primordial mixture of hydrogen and helium, a recipe that would set the stage for the next chapter in cosmic history. This process wasn't just about creating elements, it was about setting the rules for how the universe would evolve. The balance of hydrogen and helium created during Big Bang nucleosynthesis became the fuel for the first stars. Without this initial stockpile, the universe would have remained dark and lifeless. It's a reminder that even the smallest details in the cosmos, like the precise amount of helium formed, can have profound consequences. So what came next? As the universe continued to expand and cool, these light elements began to clump together under gravity, forming the first clouds of gas. These clouds would eventually collapse, igniting the first stars and lighting up the cosmos. But that's a story for another moment. For now, let's marvel at the simplicity and elegance of those first few minutes, a fleeting yet pivotal chapter in the story of everything. Imagine a universe cloaked in absolute darkness where no stars, no galaxies, and no sources of light yet existed. This was the Cosmic Dark Ages, a period that began roughly 380,000 years after the Big Bang, lasting for hundreds of millions of years. During this time, the universe was a vast, silent expanse, filled with a cooling sea of hydrogen and helium gas. It was a time of stillness, almost like a blank canvas, waiting for the first brushstroke of light to bring it to life. After the initial burst of energy from the Big Bang faded, the universe entered this era of darkness. The photons, particles of light that once filled space, had scattered and cooled, no longer able to illuminate the cosmos. Without stars or galaxies, there was nothing to produce new light. It was as if the universe itself had gone to sleep, holding its breath in anticipation of what was to come. But this silence wasn't eternal. Deep within the darkness, tiny fluctuations in the density of matter began to pull atoms together through gravity. These clumps of gas grew denser and hotter over millions of years until something extraordinary happened. The first stars ignited. Like flickering candles in an endless void, these stars pierced the cosmic darkness, ending the dark ages and ushering in a new era of light. The formation of these first stars, often called population 3 stars, was a monumental event. They were unlike any stars we see today, massive and blazing with intense ultraviolet light. Their birth marked the dawn of a universe that would soon be filled with galaxies, planets, and eventually life itself. So, what happened next? How did these first stars transform the universe from a dark, silent void into the vibrant cosmos we know today? Let's explore how their light began to shape the fabric of the universe, setting the stage for everything that followed. Long before galaxies filled the sky, the universe was a vast, silent expanse shrouded in darkness, a time astronomers call the cosmic dark ages. But this era didn't last forever. Out of the void, something extraordinary happened, the birth of the first stars. These weren't just any stars, they were the pioneers of light, known as population 3 stars. Unlike the stars we see today, these ancient giants were made almost entirely of hydrogen and helium, the raw ingredients forged in the Big Bang. Imagine a universe waking up for the very first time. As gravity pulled clumps of gas together, these massive stars ignited, flooding the cosmos with their brilliant light. It was like a cosmic sunrise, ending billions of years of darkness. But these stars didn't just illuminate the universe, they transformed it. Their intense radiation began to break apart the surrounding hydrogen atoms, a process called reionization. This marked the beginning of a new era, one where light could travel freely through space, paving the way for the universe we know today. Population 3 stars were unlike anything that exists now. They were hundreds of times more massive than our Sun, burning hotter and brighter, but their lives were short and explosive. When they died, they didn't fade quietly. They went out in spectacular supernova, scattering heavier elements like carbon and oxygen into the cosmos. These elements became the building blocks for future stars, planets, and even life itself. This incredible chain of events didn't just light up the universe, it set the stage for the formation of galaxies. The remnants of these first stars clumped together, creating the seeds of the vast structures we see today. In a way, every galaxy, every star, and every planet owes its existence to those ancient giants. They were the universe's first architects, shaping the cosmos into something far more complex and beautiful than it had ever been before. Billions of years ago, the universe was a vast, dark expanse filled with swirling clouds of gas and mysterious dark matter. Over time, the pull of gravity began to work its magic, drawing these clouds together into dense clumps. Imagine a cosmic spider spinning its web, threads of dark matter stretching across the void, creating a framework for galaxies to form. These invisible threads acted like scaffolding, guiding the gas and dust into swirling disks that would eventually become the galaxies we see today. At the heart of many of these galaxies, something extraordinary took shape: supermassive black holes. These cosmic giants, millions or even billions of times more massive than our Sun, played a crucial role in shaping their surroundings. Think of them as the architects of the galaxy, their immense gravity pulling in matter and releasing vast amounts of energy. This energy, in turn, heated up the surrounding gas, preventing it from collapsing too quickly and allowing stars to form at a steady pace. Without these black holes, galaxies might have burned through their fuel too fast, leaving them barren and lifeless. But how did these galaxies evolve over time? Did they remain static, or did they change and grow as the universe expanded? The answer lies in the intricate dance of gravity, gas, and dark matter, a dance that continues to shape the cosmos even today. Long before our solar system came into existence, the universe was a much simpler place filled mostly with hydrogen and helium, the lightest elements forged in the aftermath of the Big Bang. But something extraordinary had to happen to create the complex chemistry that makes life possible. Enter supernova, the universe's most powerful and transformative events. These colossal explosions, marking the violent deaths of massive stars, are the cosmic furnaces that forged heavier elements like carbon, oxygen, and iron, the very building blocks of planets, oceans, and even our own bodies. When a star many times more massive than our Sun exhausts its fuel, it collapses under its own gravity and then rebounds in a cataclysmic explosion. In that fleeting moment, temperatures soar to unimaginable levels and atoms are smashed together, creating elements far heavier than those found in the star's core. These elements are then scattered across the cosmos, seeding the interstellar medium with the raw materials needed for new stars, planets, and eventually life. Take, for example, the remnants of ancient supernova like the Crab Nebula. This glowing cloud of gas and dust, located more than 6,000 light-years away, is the aftermath of a star that exploded nearly 1,000 years ago. Within its swirling tendrils, we find traces of elements like silicon, sulfur, and calcium elements that would later become part of rocky planets like Earth. Without these stellar explosions, the universe would lack the diversity of elements necessary for the formation of complex systems, including the very ground beneath our feet. But supernova don't just enrich the cosmos with heavy elements, they also shape the structure of the universe itself. The shock waves from these explosions compress nearby gas clouds, triggering the birth of new stars and even entire galaxies. In this way, supernovae are both destroyers and creators, tearing down the old to make way for the new. Their impact echoes across billions of years, influencing the evolution of galaxies and the intricate dance of cosmic matter that continues to this day. So, the next time you look up at the night sky, remember that the atoms in your body were once part of a star that lived and died long before the Earth existed. Supernovae are not just distant, awe-inspiring events. They are the very reason we are here, the architects of a universe rich with possibility. Picture the universe as a vast, intricate tapestry woven together by invisible threads of gravity. This is the cosmic web, a colossal framework that stretches across the cosmos, connecting galaxies, clusters, and immense voids in a delicate balance. At its core, this structure is shaped by the gravitational influence of dark matter, an elusive substance that makes up most of the universe's mass. Like an unseen hand, dark matter pulls matter into dense filaments, creating a network of light and shadow that defines the universe on the grandest scale. These filaments, often referred to as the backbone of the cosmic web, are where galaxies and galaxy clusters gather, forming dense knots at their intersections. Between them lie vast, nearly empty regions called voids, where matter is sparse and darkness reigns. Together, these elements create a breathtaking pattern, resembling a spider's web or the branching veins of a leaf, but on a scale so immense it's almost impossible to comprehend. But how did this cosmic tapestry come to be? The story begins in the early universe, just moments after the Big Bang. tiny fluctuations in density born from quantum ripples were amplified over billions of years by gravity. Dark matter, acting as the universe's scaffolding, began to clump together, pulling ordinary matter, like gas and dust, into its gravitational embrace. Over time, these clumps grew into the filaments and nodes we see today, forming the backbone of the cosmic web. What's truly remarkable is how this structure has evolved. From its delicate beginnings in the early universe to the sprawling network we observe now, the cosmic web tells the story of time itself. Each filament, each void, is a chapter in the history of the cosmos, a testament to the forces that have shaped everything we know. And as we peer deeper into the universe, we're left wondering, how will this grand structure continue to change in the eons to come? Black holes are more than just cosmic vacuum cleaners devouring everything in their path. They are the universe's architects, shaping the very structure of existence. Picture them as cosmic engines, relentlessly driving change on an unimaginable scale. From the smaller stellar black holes born from the collapse of massive stars to the supermassive giants lurking at the heart of galaxies, these enigmatic objects have played a pivotal role in the evolution of the cosmos. When a massive star exhausts its fuel and collapses into a stellar black hole, it doesn't just vanish, it leaves behind a gravitational footprint that alters its surroundings. These black holes can merge, creating ripples in space-time known as gravitational waves, which propagate across the universe. These waves aren't just echoes of cosmic violence, they're the drumbeats of change, redistributing energy and matter in ways that influence the formation of new stars and planets. But the real heavyweights are the supermassive black holes. These titans, millions or even billions of times more massive than our Sun, sit at the centers of galaxies. Far from being mere destroyers, they act as gravitational anchors, pulling stars, gas, and dust into swirling orbits. This process doesn't just create galaxies, it sustains them. The intense gravitational forces heat up surrounding matter, generating vast amounts of energy that can ignite star formation or even halt it, depending on the black hole's activity. Think of supermassive black holes as the conductors of a cosmic orchestra. Their immense gravity orchestrates the movement of stars and gas, ensuring galaxies don't fly apart. Without them, the universe might be a far more chaotic and less structured place. And when galaxies collide, their central black holes can merge, releasing tremendous amounts of energy and reshaping the cosmic landscape. But how does this tie back to the origins of the universe? Black holes, in their own mysterious way, are time capsules. Their formation and growth are intertwined with the earliest epochs of cosmic history. By studying them, we catch glimpses of the universe's infancy, a time when matter was denser, energy more intense, and the seeds of galaxies were just beginning to sprout. Black holes, in essence, are both the architects and the storytellers of the cosmos, revealing how the universe grew from a primordial soup of particles into the vast, intricate web of galaxies we see today. As we gaze out into the vast expanse of the cosmos, one question looms larger than any other. What lies ahead for the universe? Will it continue to expand forever, stretching into an endless void, or will it eventually collapse back in on itself? These are the grand cosmic questions that scientists have been grappling with, and the answers hinge on the mysterious force known as dark energy. One possibility is what's called the Big Freeze. Picture this: the universe keeps expanding at an accelerating rate driven by dark energy. Over trillions of years, galaxies drift farther and farther apart, stars burn out, and black holes evaporate. Eventually, the cosmos becomes a cold, dark, and empty place, a vast expanse of nothingness where even time itself seems to lose meaning. It's a haunting vision, but one that aligns with current observations of the universe's accelerating expansion. Then there's the Big Crunch, a scenario that feels almost poetic in its symmetry. Here, dark energy's influence weakens and gravity takes over. The universe stops expanding and begins to contract, pulling everything back together. Galaxies collide, stars are crushed, and space itself shrinks until the entire cosmos collapses into an infinitely dense point, a mirror image of the Big Bang. It's a dramatic end, but one that raises tantalizing questions about whether this cycle could repeat itself, leading to a new universe born from the ashes of the old. And let's not forget the Big Rip, perhaps the most explosive of the three. In this scenario, dark energy becomes so dominant that it overwhelms even the forces holding atoms together. Galaxies, stars, planets, and eventually even molecules and atoms are torn apart in a cosmic cataclysm. The universe doesn't just fade away, it shatters. It's a startling reminder of how fragile the fabric of reality might truly be. These theories aren't just abstract ideas. They're grounded in the observations and calculations of physicists studying the cosmos. Dark energy, the enigmatic force driving the universe's expansion, plays a starring role in each of these scenarios. Its behavior, whether it strengthens, weakens, or remains constant, will ultimately determine our cosmic fate. So, what does all of this mean for us here and now? It's a humbling thought to consider that we're living in just a fleeting moment in the universe's unimaginably long timeline. From its fiery birth in the Big Bang to its potential end in the cold embrace of the Big Freeze, the collapsing drama of the Big Crunch, or the explosive finale of the Big Rip, the universe's story is one of constant change and transformation. As we reflect on this journey, it's impossible not to feel a sense of awe. The same forces that shaped the cosmos billions of years ago continue to shape its destiny today. And while we may never know for certain how the universe will end, the pursuit of these answers reminds us of the beauty and mystery that surrounds us and the incredible privilege of being here to witness it. To uncover the mysteries of the universe's origins, scientists rely on an extraordinary array of tools and techniques, each designed to peel back the layers of time and space. At the forefront are powerful telescopes like the James Webb Space Telescope, which acts as a cosmic time machine, capturing light from the earliest stars and galaxies. By observing these ancient signals, we're able to glimpse the universe as it was billions of years ago when the first structures began to form. But telescopes aren't the only instruments in this grand quest. Particle colliders like the Large Hadron Collider recreate the extreme conditions of the early universe, allowing us to study the fundamental particles and forces that shaped everything we see today. Simulations also play a critical role, offering a virtual window into the past. Supercomputers process massive amounts of data, modeling the evolution of the universe from its first moments to the sprawling cosmos we inhabit now. These simulations help us test theories and make predictions, bridging the gap between what we observe and what we can infer. Together, these tools form a toolkit that's as diverse as the universe itself, each providing a unique piece of the puzzle. Looking ahead, the future of cosmic research is brimming with potential. New telescopes, more advanced colliders, and even larger simulations are on the horizon, promising to deepen our understanding of the universe's origins. With every discovery, we move closer to answering the ultimate question: how did it all begin? The study of cosmic origins doesn't just unlock the secrets of the universe, it also invites us to grapple with some of the most profound questions humanity has ever asked. What does it mean to exist? Is time a fundamental feature of reality, or is it something our minds impose on the cosmos? These are the kinds of questions that philosophers and scientists alike have wrestled with for centuries. As the physicist Stephen Hawking once said, "The universe doesn't allow perfection." This simple yet striking statement reminds us that the cosmos is not some static, unchanging entity. It's a dynamic, ever-evolving system, and we are part of that story. Think about it, when we look back to the Big Bang, we're not just studying an event that happened billions of years ago. We're peering into the very origins of time itself. Saint Augustine, a philosopher from the 4th century, famously pondered the nature of time, asking, "What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know." Even today, time remains one of the most mysterious and debated concepts in both science and philosophy. Is it linear, cyclical, or something else entirely? And what does it mean for us to exist within its flow? These questions aren't just for scholars and scientists, they are for anyone who has ever looked up at the night sky and wondered, why are we here? The philosopher Immanuel Kant once described this sense of awe as the starry heavens above me and the moral law within me. That duality between the vastness of the cosmos and the intimacy of our own existence captures the heart of what makes cosmic origins so fascinating. It's not just about understanding the universe, it's about understanding ourselves. And here's the thing, you don't need a degree in astrophysics or philosophy to feel the weight of these questions. They're woven into the fabric of our curiosity. Whether you're watching a documentary about the Big Bang or simply staring at the stars on a quiet night, you're engaging with the same timeless questions that have driven humanity's quest for knowledge. So, the next time you find yourself wondering about the meaning of existence or the nature of time, remember, you're not alone. These questions connect us all across cultures, generations, and even the vast expanse of the cosmos itself. Mathematics is often called the language of the universe, and for good reason. It's the tool that allows us to decode the cosmos, translating the chaos of the unknown into patterns we can understand and predict. Think about it, without math, we wouldn't have the equations that describe how planets orbit stars, how light bends around massive objects, or even how time itself behaves under extreme conditions. Take Einstein's theory of general relativity, for example. His equations didn't just describe gravity as a force, they redefined it as the curvature of spacetime itself. This mathematical framework didn't just explain what we already knew, it predicted phenomena we hadn't even observed yet, like black holes and gravitational waves. And decades later, those predictions were confirmed, showing just how powerful math can be in uncovering the secrets of the universe. But math isn't just about describing what we see, it's about revealing what we can't. It's a bridge between the observable and the unimaginable. For instance, consider the equations that govern quantum mechanics. They describe a world so strange and counterintuitive that even the scientists who pioneered the field struggled to make sense of it. Yet, through math, we've been able to predict the behavior of particles at the smallest scales, leading to technologies like semiconductors and quantum computers. It's as if the universe is whispering its deepest truths to us through numbers and symbols, and math is the key to deciphering that cosmic code. So, what does this mean for our understanding of the universe's origins? If math can reveal the behavior of black holes and the rules of quantum particles, could it also help us peer into the moments before the Big Bang? Some physicists believe that by pushing the boundaries of mathematical models, we might uncover clues about what, if anything, existed before time and space as we know it began. It's a tantalizing possibility, one that suggests the universe's story might be written in equations waiting to be solved. And as we continue to explore, math remains our most reliable guide, lighting the way through the darkest corners of the cosmos. But even as we push the boundaries of science and technology, there are questions that seem to hover just beyond our grasp. Imagine standing at the edge of a vast, endless abyss peering into the darkness. You can see shapes, flickers of light, but the deeper truth remains shrouded in mystery. This is where we find ourselves when we try to unravel the universe's origins. The tools we have, telescopes, particle accelerators, even our most advanced theories only take us so far. beyond that point, the cosmos seems to whisper, "Not yet." Some mysteries might remain unsolved, not because they're unknowable, but because our current understanding and technology simply don't have the capacity to probe that deeply. And yet, there's something profoundly beautiful about this. The unknown isn't just a void, it's a frontier, a reminder that the universe is far grander and more complex than we can fully comprehend. It invites us to keep exploring, keep questioning, and to embrace the wonder of what we don't yet understand. After all, isn't that what drives us forward? The curiosity to know more, to see more, to dream bigger. Even if we never fully answer every question, the journey itself, the act of reaching for those answers, is where the magic lies. It's not just about the destination, it's about the awe-inspiring journey through the cosmos, one step at a time. The universe's origins have always been a profound mystery, one that has sparked not only scientific inquiry but also deep spiritual and philosophical reflection. Across cultures and throughout history, humanity has sought to answer the same fundamental question: how did everything begin? This quest has given rise to a fascinating intersection between science and spirituality, where empirical evidence meets the intangible realm of belief. Take, for example, the creation myths of ancient civilizations. In Greek mythology, the universe emerged from chaos, a formless void that gave birth to the first gods. The Norse believed in a primordial realm of ice and fire colliding to create life. In Hindu cosmology, the universe cycles through endless periods of creation and destruction, guided by the breath of the divine. These stories, though vastly different, share a common thread: a desire to explain the inexplicable, to find meaning in the vastness of existence. Modern science, with its tools and theories, offers a different lens. The Big Bang Theory, supported by observations of cosmic microwave background radiation, paints a picture of an expanding universe born from an infinitely dense point. Yet, even here, questions linger. What existed before the Big Bang? What lies beyond the observable universe? These are questions that science, for now, cannot fully answer, leaving room for wonder and interpretation. This is where spirituality steps in, offering a different kind of understanding, one that doesn't rely on equations or data, but on intuition, faith, and tradition. For many, the cosmos is not just a collection of stars and galaxies, but a reflection of something greater, a divine order or purpose. The harmony of the universe, its intricate laws and patterns, can feel almost sacred, as if pointing to a higher intelligence or design. What's remarkable is how these two perspectives, science and spirituality, can coexist and even complement each other. Science seeks to uncover the mechanisms of the universe, while spirituality explores its meaning and significance. Together, they form a richer tapestry of understanding, one that acknowledges both the physical and the metaphysical. This shared quest for answers unites humanity, transcending boundaries of culture, time, and belief. Whether through a telescope or a sacred text, we are all searching for the same truth: the story of our origins and ultimately our place in the cosmos. And perhaps in this journey we find not only knowledge but also a deeper connection to each other and the universe itself. Curiosity is the spark that lights the fire of discovery. It's what drives us to look beyond what we know, to question the unknown, and to seek answers to the mysteries of the cosmos. Think about the story of the Big Bang. It wasn't just a sudden, random revelation. It was the result of decades of relentless curiosity. Scientists like Georges Lemaitre and Edwin Hubble didn't just accept the universe as it appeared, they asked questions. Why are galaxies moving away from each other? What does this mean about the origins of everything? Their curiosity led them to piece together the evidence, culminating in the groundbreaking idea that the universe began with a massive explosion of energy and space itself. But curiosity isn't just for scientists in labs or astronomers peering through telescopes. It's a trait we all share. Every time you look up at the night sky and wonder what's out there, you're tapping into that same instinct that has propelled humanity forward. It's what makes us explore, invent, and imagine. Without curiosity, we'd still think the Earth was flat or that the stars were just tiny lights fixed in a dome above us. So, what about you? What cosmic questions keep you up at night? Maybe it's the idea of black holes, those mysterious regions where gravity is so strong that not even light can escape. Or perhaps it's the search for extraterrestrial life. Are we truly alone in the universe? Whatever it is, let that curiosity guide you. Because every great discovery, every leap in our understanding of the cosmos starts with a simple question: what if? The universe is vast and there's so much we still don't know. But with curiosity as our compass, we're always moving closer to the truth. From the unimaginable moment of the Big Bang to the vast, intricate web of galaxies we see today, the story of our universe is one of endless wonder. We've traced the birth of space and time, watched stars ignite from swirling clouds of gas, and pondered the mysteries of dark matter and dark energy. We've even ventured into the mind-bending realms of the multiverse, where countless universes might exist beyond our own. Each discovery reminds us that the cosmos is far more expansive and mysterious than we could ever fully comprehend. Carl Sagan once said, "We are a way for the cosmos to know itself." And in many ways, that's what this journey is all about. Not just understanding the universe, but understanding our place within it. Every question we answer leads to new mysteries, and every discovery sparks new curiosity. The universe is a story still being written, and we are all part of its unfolding narrative. So what's next? The cosmos is full of secrets waiting to be uncovered, from the nature of black holes to the possibility of life beyond Earth. The beauty of science is that it's a never-ending adventure, and there's always more to explore. If you've enjoyed this journey through the origins of the universe, don't stop here. Dive deeper, ask questions, and keep looking up at the stars. And if you've got thoughts or theories about the cosmos, share them in the comments below. I'd love to hear what you think. If you're as fascinated by the universe as I am, hit that subscribe button and join me for more cosmic explorations. Together, let's continue unraveling the mysteries of existence, one discovery at a time. After all, the universe isn't just out there, it's within us too.